Modern computing systems, from complex machine learning networks to advanced physics engines, are built using continuous mathematical models. Executing those complex end goals requires a stable architecture. Before a system can train a neural network, it must first execute a predictable mapping of raw inputs to specific outputs. This coordinate plane shows four foundational models: functions, linear equations, quadratics, and exponentials. These shapes map to specific computational uses. The straight line drives regression models. The parabola solves optimization problems. The exponential curve scales data visualization. We will build these four geometric primitives from scratch to understand the mechanics of computer science. Bypassing these algebraic models makes higher-level algorithms difficult to implement. Visual fluency here is a necessary step before attempting calculus. We begin with the function. A function is a mathematical rule that assigns exactly one output, y, for every input, x. If we define our function as x squared, an input of 3 inserted into the box yields exactly 9. Not all inputs are valid. The set of allowable inputs for a function is its domain. This is a graph of the function 1 over x. Because dividing by 0 is undefined, x can never equal 0. For the square root of x, the domain is bounded. Inputs must be 0 or greater. Passing an input outside of these domain boundaries causes the logic to break, resulting in a runtime error in software. We can chain these rules together using a process called composition, written as f of g of x. In composition, the output of function g becomes the input of function f. This is the mathematical equivalent of software pipelining. Understanding mapping rules and domain boundaries supports the engineering of stable system architecture. When a system scales with a constant rate of change, we use linear equations. This linear model's constant change is the slope, measured between 2 points. A positive slope increases, negative decreases, and 0 is horizontal. This equation is y equals mx plus c, where c is the y-intercept. Linear systems follow specific interactive rules. Parallel lines have identical slopes. Perpendicular lines invert and negate each other. Multiplying their slopes together equals -1. Finding the points where the line crosses the zero axes by setting either x or y to 0 establishes the boundary conditions. This constant mathematical relationship drives the linear regression models used throughout data analysis. Identifying these linear bounds and intercepts is a requirement for writing predictive data visualization algorithms. Real-world data often requires nonlinear scaling. Squaring an input term forces the system's output to curve, creating a quadratic equation. This quadratic equation visualizes as a parabola. The highlighted x-intercepts show where the curve reaches 0. To find these roots, the quadratic formula's plus or minus variable splits to isolate both coordinates. These roots indicate where a computational system's value reaches a ground state. Once the roots are established, we identify the valley of the curve, the vertex. The calculation to pinpoint this extreme point is defined as x equals -b divided by 2a. This vertex formula locates a system's maximum or minimum state. In machine learning, algorithms rely on cost functions to measure error rates. Finding the minimum of a parabola minimizes that algorithm's cost function. These quadratic relationships provide the mathematical framework for physics simulations and algorithmic optimization. To model rapid data scaling, we examine functions where the variable itself is the exponent. This graph shows an exponential function. It starts flat, followed by rapid upward growth. The interactions of these numbers follow specific rules. For example, multiplying two exponential terms with the same base requires adding their exponents. To counter this growth, we use logarithms, the direct inverse of an exponential function. Visually, a steep exponential curve reflects across a diagonal line to reveal the flattened logarithmic curve. While exponentials grow data, logarithms deconstruct and compress that growth. Logarithmic rules allow a computer to convert multiplication operations into simple addition. Using logarithms to compress data and simplify operations is a method for achieving algorithmic efficiency. We have built a conceptual ladder: mapping rules, linear changes, quadratic curves, and inverse exponential scaling. This visualization shows all four models operating simultaneously. They function together as a unified mathematical ecosystem. These four paradigms provide the geometric vocabulary required to render and optimize software. Even a complex machine learning pipeline can be mathematically disassembled into these basic geometric primitives. Complex systems emerge from these simple, functioning rules. Fluency with these foundational models provides the base for mastering calculus and more advanced computational logic.